So we had one class missed due to the computer issues, and today is the next class of the thermal worksheet solution. So we're going to see some problem from here, and we'll also take requested problem from the students as well. I'm now starting for question number 14. Let's have a look. The EMF generated for a thermocouple in a thermocouple thermometer may be used to measure the temperature, may be used for the measurement of temperature. Figure 7.1 shows the variation of temperature T to the EMF E. So we have an EMF versus temperature, Kelvin temperature scale, which looks like a graph. By reference to figure 7.1, state two disadvantages of using this thermocouple when the EMF is about 1 millivolt. So one of the disadvantages is obviously that 1 millivolt measured out of the thermocouple can lead to two confusing answers. It could be a temperature between 300 and 400 Kelvin. It might also represent a temperature somewhere near to 700 Kelvin, because we have 1 millivolt available for both of these reading. So that's one confusing part. The other problem that we have that the thermometer has. What is the other disadvantage? What is the other disadvantage that we can have? We can see that the scale is non-linear, so that can also pose a problem for the thermodynamic equation. But provided that we have a graph, extrapolation can prove to be easier. But we don't have the equation of the curve, so which should be tricky. I'm going to look at the mark scheme to find out the second problem. And question number B is also pretty interesting. We have a look over here. You see, variation is nonlinear. Yeah, that's one problem. And two possible temperature. Okay, pretty much what I said. The examination report says significant number of candidates misread the question and wrote down the general disadvantages of a thermocouple rather than the disadvantages apparent on figure 7.1 when the EMF is about 1.0 millivolt. So yeah, students tend to not read the questions whenever they're excited or think that they'll know the answer. In question number B, it says an alternative to the thermocouple thermometer is the resistance thermometer. So two advantages that a thermocouple thermometer has over a resistance thermometer. Two advantages that a thermocouple thermometer has over a resistance thermometer. I think this is a perfectly theoretical answer, nothing related to this graph. Just you have to know properties of resistance thermometer and thermocouple thermometer. For those of you who do not know what a resistance thermometer is, a resistance thermometer is basically a thermometer that relies upon the change of resistance of a specific substance with respect to temperature. If we use metal or an alloy of multiple metals, this is going to work like as temperature goes higher, the resistance is also going to go higher. So if you plot a graph of resistance versus temperature, you're going to get an increasing graph. How the gradient is going to work out? Should you have a straight line gradient? Should you have a decreasing gradient, increasing gradient curve? In most cases, it is decreasing gradient. But if we want to make it a straight line, we might actually have to see in the composition of the alloy. But it's going to be a positive gradient graph anyway, for if we use some metal alloy. Whereas on the other hand, if we use some semiconductor material, which actually make up the thermistor, which is thermal resistor, these things are usually NTC. NTC stands for negative temperature coefficient kind of material, which means as temperature goes higher, their resistance is going to go lower. So those graphs are going to be decreasing graphs. So more value on the left side of the graph, less resistance on the right side of the graph. But then again, the graph can be of different shapes. Usually the resistance versus temperature graph for thermistor materials is decreasing gradient. So you have a pretty steep drop at the beginning, and then the decrease slowly dies out. So it slowly loses gradient. That's all I know. But for this question, I would like to see for the mark scheme what they have over here. I really do not recall the actual answer of this question. So if I was solving this worksheet, I'm going to put a star mark over here to have a revision every chance that I get to whenever I come across this worksheet for future references. It says that small thermal capacity measures delta theta of small object or short response time. Readings taken at a point or physically small can be used to measure temperature difference. No power supply required, etc. Any two, 1 mark each. Okay. So I'll explain these parts for you. First of all, it says small thermal capacity or measured delta theta of a small object. What this actually means that whenever we have a thermocouple thermometer, the thermocouple thermometer is usually built using a very simple mechanism. We have one metallic wire and we have a second metallic wire which are joined on the two sides. one of the side is what we call the hot junction, the other one is what we call the cold junction. And whenever there is a temperature between these two junctions, if we place a voltmeter anywhere in the wire, over here, in some cases we can also choose to attach a voltmeter just like that. I mean, the cold junction itself can be the voltmeter, so you can even connect a voltmeter right over here. So voltmeter itself works as the cold junction. You don't have to place it over here. That's going to give you the temperature voltage measurement, which can be read into, or which needs to be converted into the temperature of the hot junction, actually temperature difference of the hot junction. Now, usually the thermocouple thermometer, a typical thermocouple thermometer looks like this. Let me just show you one of the images. Yeah, for example, this one. This thermocouple thermometer, this is the most common type of thermocouple thermometers. Some of these things actually have two wires coming out of them. I believe in those cases, they can actually signify the cold and the hot junction both. But most common thermocouple thermometers actually come up with a single wire, where the room temperature is the cold junction temperature, which is recorded within the device, and this long wire actually gives us the hot temperature junction. And you can see that at the tip of this object, there's a very small tip over here. We can just touch this part of the of this metal rod to the hot object that we want to measure, and by taking even a small bit of heat energy from the source, it can give you the reading pretty well. So the amount of material that we actually have to heat up to get a reading out of a thermocouple thermometer is actually very small. Unlike other type of thermometers, for example, resistance thermometer or even mercury in glass thermometer, where you have to heat up the entire thermometric fluid or thermometric object to the temperature of the hot body to get to there. So this point, what it says that thermal capacity, small thermal capacity, it actually means that the amount of material that you have to heat up to get your steady reading of the hot object is very small. So mass of the material is small, which actually requires less heat to be absorbed from the hot object. And also it gives your temperature reading pretty fast. So all of these points individually is going to give you 1 mark. You show, so because all of these points actually responds to come up to 4 to give us one specific advantage, that it gives us a short response time. And then it comes up, the readings can be taken at a point or a physically small area. So this is actually useful whenever we have an object that has a range of temperature from the hot source. For example, let's say if you are trying to heat up a metallic object, or if you're trying to, let's say, cool down some glass for some very special purposes, different location of the glass material, depending upon the distance from the furnace, can have different temperature. Part of the glass material, which is when in the manufacturing process, which is close to the or inside the furnace, is going to have one temperature. As you slowly pull it out from the furnace, you're going to have different temperature as it cools off, being in contact with the atmosphere. Thermocouple thermometer can be used to measure the exact temperature of individual different locations, because the size of the sensor is actually pretty small. So it can be used for localized temperature. So you can also use that word which you learned in your O levels, that it can measure temperature at a specific location, or it can take localized temperature. That's your second thing. Number 3 says can be used to measure temperature difference. Well, it's obviously how the thermocouple thermometer works. And then no power supply is required. This is also pretty interesting. Typical thermocouple thermometer actually produces a voltage of its own. So the way the thermocouple thermometer works, that the figure that I just showed you, there is the hot junction, there is the cold junction, and the temperature difference between these two junctions actually produces a voltage across within this voltmeter. So that EMF generated within the coil can be used to read of the temperature, and that can work pretty easily. So in many cases, we do not need a physical battery source, but in certain other scenarios, many thermocouple thermometers actually require a physical battery for a better functioning purpose. But it can be designed to work with the inherent voltage generated within thermocouple mechanism itself. So this question doesn't have any specific answer. They have given the marks in terms of example, so you can write any 2 points out of this. For example, so we can think of other relevant points which are acceptable and logical, that they're going to be also accepted. That's the whole point of giving the example part. If you have a look at the marks, examination report, inappropriate answers frequently included better range or better accuracy or greater sensitivity. These are all considered to be inappropriate. all answers based on small physical size and thermal capacity were expected. The reason we are not accepting these things, I mean, it's not that these values are not acceptable, or that these are not true for thermal thermometer. The key part that you have to distinguish is that the question asked us that what is the so this question actually asked us that what would be the advantage of a thermal thermometer over a resistance thermometer. A resistance thermometer also has a pretty high range. It can be pretty sensitive, and it can be also work for it can also have, what is the other property, it can also have greater sensitivity, because resistance thermometers, the reason resistance thermometers have a pretty large range is because the idea is that we're going to increase the temperature of the material, and we're going to measure the resistance variation of the material over different range of temperatures. As long as that material does not melt for the applied temperature, a resistance thermometer usually performs pretty well for the whole range. So if you can make a material that has a really high melting point, you can also use a resistance thermometer for a really large range of temperature measurement. So that is also an advantage within the resistance thermometer, which is also applicable for thermal thermometer as well. So that property actually doesn't prove a distinction or a difference between the two choices of the thermometer. This question was that two advantages that a thermocouple thermometer has over a resistance thermometer. That's why those 3 points were not appreciated to be a correct answer for this question. Did you understand this part, everyone?
Yes, sir.
Yes, sir.
এই কোশ্চেনটা আমি definitely স্টামাক করে রাখতে এই কোশ্চেনটা actually frequent রিভাইজ করা দরকার আছে, otherwise if you, because this is not a theoretical, this is not a mathematical answer, and this is something related to your O levels, and these stuffs are actually not in detail taught in your syllabus. Even if you turn up your actual CAE by Ender's book, you are not going to see too much description of this individual type of thermometers. So it's important that you take note from, or if you take specific care out of the examination from the mark schemes. So I would definitely stomach this question if I was solving this paper. Question number 15 is actually pretty simple. You can put all the numbers over here and get the value out of it. But still, I'm going to do this problem because of number C. How many strokes are going to be needed? So let's try and solve this problem. First of all, question number 15 says the air in a car tire has a constant volume of this much meter cube. Pressure of this air is 2.9 into 10 to the 5 Pascal at a temperature of 17 degrees Celsius. The air may be considered to be an ideal gas. State what is meant by an ideal gas. You just write the definition over here. The usual way we define an ideal gas is by the ideal gas equation. So when, if you are writing that, you can choose to write, you can either choose to write a variable based equation where you have to eventually define which or what is the physical meaning of all those variables, or you can directly choose to write a word equation. If I was writing this answer, I'm going to write it this way. A fixed amount of gas that follows this ratio pressure, I'm going to write it in word. So I'm going to first give a division line, so something like that. So that follows pressure into volume divided by absolute temperature. Don't write short form. The gas, which for a fixed amount follows this ratio to be constant at all values of those three variables, is defined to be an ideal gas. Or you could write that the a fixed amount of gas that follows the ratio PV by T to be constant at all values of PV or T, where P equals to pressure, V equals to volume, T equals to the absolute temperature, is an ideal gas. Ideal gas is defined by this ratio. So for a fixed amount of gas, this ratio has to be constant no matter what pressure, volume of temperature, absolute temperature that you apply it to. So you can write it in your own fashion, no big deal, but it's important that if you're using an equation, you have to specify which variable means what. And if you are not writing into an equation, if you just directly go for a word equation like that, word fraction like that, you can skip that part. It's your choice, however you feel comfortable with it. Number B says calculate the amount of air in mole in the tire. So that's pretty simple. We're going to use PV equals to nRT. Let me calculate this number by placing all the values over here. I'm going to choose a bit smaller thickness for this pen. This is actually pretty thick. So 2.9 into 10 to the power 5 multiplied by 3.1 into 10 to the power minus 2 should be equals to n into 8.31 into 290. 70 degrees Celsius converted into 10 Kelvin gives you 290. So give me the number that you get for this thing up to a couple of decimal places. I mean, a big number of decimal places, 3-4 decimal places. What do you get? 2.9 into 3.1, 2.9 into 3.1, 10 to the power 3 divided by 8.31 divided by 290. I'm getting 3.7304. Is it okay? So since all the numbers that we have over here are in 2SF, might as well be a good idea to write the final answer in 2SF as well. So I'm gonna only write 3.7 mole only. If you choose, if you want, you can write 3.73, no big deal. It's perfectly all right, acceptable, no big deal. Answer match na korle amake boilo. I am not impervious to mathematical error. I pretty often do error in my calculation. So if I did make an error, please let me know about it. Number C, the pressure in the tire is to be increased using a pump. On each stroke of the pump, 0.012 mole of air is forced into the tire. Try to understand this thing. We are now going to increase the pressure of the tire. So we're now going to start to put using a pumper, and we're going to put in air within this tube or within this tire. For each stroke, we're entering this many mole of air into the tire. Calculate the number of strokes of the pump required to increase the pressure to this much Pascal at a temperature of this much. Now, what is important for you to consider that in this question, they have already told us that the car tire has a constant volume. This is an important bit. Having a constant volume essentially means that our volume is going to be constant. So, and the temperature in this case is actually rising. Earlier we had 70 degrees Celsius. Now we have 27 degrees Celsius. And also the new amount of gas should have a different number of moles within itself. So here is the deal. We are trying to calculate how many number of strokes should we require to get this variable present. So what we can do, let's assume that we did all the required number of strokes, and currently the entire tire, the whole tire is filled up with gas with this specification. So this is the pressure of the new pressure. This is the volume, which is constant, and this is the new temperature. So let's try to calculate how many moles of gas should be within the tire once the pumping is done. So if we go for the same equation, PV equals to nRT, we can calculate the value of n, which is gonna be 3.4 into 10 to the power 5 multiplied by 3.1 into 10 to the power minus 2 divided by, this is R, 8.31 into 300. দেখো তো এটা কত আসে? No. I'm getting 4.2278. So this is the new number of moles that we're going to require. So the difference of mole number that we have to actually put in would be that variation of these two. So 4.2278. The reason I actually kept this many big numbers, because the actual number that we're putting in by each stroke is actually pretty small. This goes up to the third decimal place. So just for the sake of convenience of my future calculation, I wrote this number in that main decimal place, which is going to come in handy. You'll see pretty soon. So 3.7304. This gives you a number, and then number of strokes, let's say this is X, would be equals to 4.2278 minus 3.7304. So we're gonna get 0.4974. So number of strokes is gonna be 0.4974 divided by 0.12. This is a point where you have to apply a certain judgment. I'm getting 41.45. Now my question is, what should be your number over here? Should you write this as 41 or should you write this as 42?
42.
Why not 41?
41 দিলে তো প্রেসার ইনক্রিজ করবে না।
Correct. 41 দিলে আমাদের প্রেসার বা টেম্পারেচার এক্স্যাক্টলি এই ভ্যালু পর্যন্ত রাইজ করবে না। We want to make the final pressure and temperature up to this value. So if we surpass beyond 41.45, we're gonna get above that. But the question is that we're trying that. Calculate the number of strokes of the pump required to increase the pressure to this much value at least. So applying this many strokes would be the perfect value. But when we were considering strokes, we are not actually considering fraction of strokes because our stroke is usually means all the way down force of the whole thing, of the whole pumper. So that's why we have to apply 42 strokes. If it was even 41.1, I would still go for 42. Because by applying 41, we cannot reach that pressure and temperature. By applying more than 41, we can get there. So the correct answer over here is going to be 42. Have a look at the mark scheme. Did they choose 42 as well? This number 15. Hey, yes. So if we do their calculation, where they actually went for only 3SF values for the mole calculation, they actually got 0.5 divided by 0.012, which gives us 41.66, which gave them 42. Must round up for mark. If we look at the examiner's report, it says in the majority of the calculation, the amount of gas at the new pressure was calculated correctly. However, a significant minority used the equation PV by T equals to constant, thus assuming no change in the amount of gas. Having determined the new amount of gas, many failed to calculate the change in the amount before finding the number of strokes. Oh, so many students actually, according to the mark scheme, what it means, that many students actually found out this value and divided this now. Many students actually did find out this new mole number, and then divided this new mole number by 0.012, which was not the purpose of the question. We have to find out how many would be required to reach up to the new state from the initial state. So many students apparently forgot to do the subtraction. Rookie mistake, but yeah, mistake nonetheless. Just be careful about that so that you don't go for that kind of mistakes. So that's that to make sense for how these problems are done. 16 is actually pretty simple. I would like you please to try that. If you can solve it, I'll help you for that. Number 17. Number 17 is a question about the thermometry. Not thermometry, I mean, it's actually about the heat transfer process. So I'm gonna help you to make sense of this, what is happening over here. Determine related heat of fusion, some crash tests. Did we discuss this problem earlier?
No, sir.
No, okay. So some crash ice at 0 degrees Celsius is placed in a funnel together with an electric heater as shown in figure 2.1. We have crash ice, we have a heater, we have a joule meter, we have a supply, funnel, heater, beaker. The mass of water collected in the beaker is a measured interval in a measured interval of time is determined with the heater switched off. The mass is then found with the water switched on. The energy supplied for the heater is also measured. For both measurements of the mass, water is not collected until melting occurs at a constant rate. The data shown in figure 2.2 are obtained. This line is a very important line. For both measurements of the mass, water is not collected until melting occurs at a constant rate. It means we have to observe the dripping of the water out of the funnel to reach an uniform rate. So how many drops are falling? Once you visually confirm that the water drops are falling at a constant rate or an uniform rate, only then should we place the beaker under the funnel, start the stopwatch, wait, measure the time, and then as we stop the stopwatch, we should remove the beaker. So switching off the joule meter actually doesn't stop the flow of water. So physically you have to put in the beaker under the funnel, start the stopwatch, and keep it there for a certain duration of time for which you want to do. For example, in this case, this is 10 minutes and 5 minutes. And at that specific, after the specific amount of time interval has passed away, you have to physically remove the beaker carefully, not to splash water, not to spill water. And then you have to measure the masses. So one thing that I need to make sense that here they have given us two different measurements. Have a look at the table. But they are showing us that when heater is switched off, mass of water melt out of the whole body is 16.6 gram, where energy supplied to the heater is 0, and they measured this amount for a duration of 10 minutes. Whereas when the heater was switched on, we got 18,000 joules supplied. We got a total amount of mass of ice melt was 64.7 gram, and we run that experiment for 5 minutes. Now, the question number 1 is state why mass of water determined with the heater switched off. This is the part that is very simple, which we discussed earlier, that for this whole experiment, our experiment apparatus setup temperature is 0 degrees Celsius, the melting temperature of ice. So obviously extra heat is going to enter into the system from the surrounding, which we need to take care for. So other than physically trying to calculate out how much was done, we're going to measure how much error does this cause to our experiment. So without turning on the heater or having the heater switched off, we let the atmospheric heating do some melting to our apparatus setup. And what we found out, in a duration of 10 minutes, the atmospheric heating does a melt of 16.6 grams. So we did this for a pretty long time because we wanted to measure the amount of water to be significantly large. That's something that you should know from experiments, that whenever we measure something for a bigger number of times or bigger number of duration, the error becomes less affecting for the measurement. And when we switched on the heater, we did the same thing, but this time we collected the time amount for 5 minutes. If you wonder why is that, there can be a lot of different reasons. Maybe the funnel was not big enough to hold enough crushed ice to run the experiment for 10 minutes while the heater was still ensured to be put underneath the crushed ice. I mean, because we are continuously melting the heater. And also within 5 minutes by when the heater was turned on, we actually could collect a significant good mass of water, 64.7 gram. So it didn't make sense to go for a bigger amount. The reason we have taken 10 minutes over here is to collect a bigger amount of water. The reason we are not going for a bigger time over here because we have enough amount of water, and maybe the apparatus setup does not accommodate for a 10-minute interval duration whenever the heater is switched on, maybe for the size of the funnel, which is a pretty likely cause. But whenever we're going to do the math, it's important that we should equate both of this time. What it means that atmospheric heating does this much mass of water melt, atmospheric heating, in 10 minutes. And when the heater was switched on, within this amount of water, 64.7 gram of water, we had both the heater melt water, we had also the atmospheric melt water. But in this case, atmospheric melt water was done for 5 minutes. So if we just do a quick math, if atmosphere exclusively melts 16.6 gram in 10-minute duration, in a 5-minute duration, it's going to melt 8.3 gram. I'm just dividing by 2, which goes on to mean that within this 64.7 gram of water that we collected when the heater was switched on, 8.3 gram of water was actually melt from the atmospheric heating, and the remaining water was exclusively melt from the heater. So this 18,000 joule of water, 18,000 joule of heat energy that was supplied by the heater was responsible to melt less than 64.7 gram because atmosphere also did some melting. How much did the atmosphere melt? We wanted to measure it. That's why we had to take the first reading. So then it says suggest how it can be determined that the ice is melting at a constant rate. We just talked about that. What we have to do, we have to observe that.
Sir, আপনার কথা কেটে কেটে আসছে।
How come? কখন থেকে?
অনেকক্ষণ থেকেই স্যার।
হ্যাঁ
না স্যার, আপনার
আমাদের সমস্যা ছিল।
Zara, would you check your connection? Did Zara just leave? No, Zara is here. Would you check your connection or try
I
to
didn't.
get be here? See if you can get a seat closer to the Wi-Fi connection. If you have a Wi-Fi connection, then that could possibly solve it. I don't have any
All right,
incoming
sir.
phone calls right now, so I hope I don't have any interference so in my system. Sit close to the Wi-Fi. That's one solution, or try to make sure that no one in your house is using a large bandwidth within your internet connection. That's solution number two. And I don't know of any other source that I can prove a solution for if the problem persists. These are two most common solutions that usually works. Okay. So number two, search how it can be determined that the ice is melting at a constant rate. This is actually pretty simple. We observe the dripping of the water, and when the water falls down at a visibly uniform rate, then we understand that the ice is melting at a constant rate. The language you can look it up in the Mars scheme and try to make sense with it, which is pretty simple. Calculate a value for the special inhibition of ice. It's pretty simple. All that you have to do, you have to show 16.6 divided by 2 equals to 8.3. It's good if you show that. And then 64 minus 7 minus 8.3 equals to mass, and then E equals to MLF. So directly go for the calculation. There is a 3 mark for here. What is important that over here the energy was given in 18,000 joule, but the answer they are expecting the answer in kilojoule per kg. So be careful to look at this final unit that they have already prescribed. In some cases they give these units, in some cases they don't. So if they provide this unit, you have to take care for the multiplier that they have over here. So just make sure that you divide the final answer by 1000 to get your answer in kilojoule unit. I'm not doing this working for you because I just explained it pretty well, I believe. So you try this, you still get stuck, you can ask me. I'm gonna show you in some other time. So I'm a bit curious to find out the wording that they have used for those two parts. What is the number of the question? This was number 17. Have a look. B1 says to make allowance for heat gains from the atmosphere. Okay. Number two, example, constant rate of production of droplets from funnel, constant mass of water collected per minute in beaker. Any sensible suggestion? 1 mark. And this is given as an example. So other acceptable explanations could be also accepted. Acceptable, accepted, yeah. Redundancy. Anyway, so in B2 it says, all too frequently the suggestion did not include how it would be known that the rate is constant. Common answers include statements such as weight of the beaker at regular intervals or count the number of drops per minute. Okay, you might wonder that weight the beaker at regular intervals and count the number of drops per minute. Why shouldn't these be acceptable answers? Because this is half the answer. You can choose to do this, but then you have to do a bit of a comparison, give a statement that leads to a decision. For example, weigh the beaker at regular intervals, and if the increase of weight is equal for every equal time interval, then we know it's a constant rate. Yeah, you weigh the beaker, then what? How do you pick up your decision that whether it is increasing uniformly? You have to say that, or count the number of drops per minute, and if it is the same number of drops over a couple of minutes or over a duration of over 3-4 minutes, then we know the rate is now uniform. So only counting doesn't give you a decision. You have to count, compare the numbers, and if they are same over a duration of time, then you know that you are good to go. So you have to complete your information. These two statements are not wrong, but they are simply incomplete in terms of what you are trying to achieve. So question number 18, let's say pretty simple. Just put numbers. This question is a bit of a theoretical question. This is actually pretty simple. Okay, this is actually pretty nice. Okay, let me just explain this part. I mean, how do we answer this part of the question? Have a look at the structure of this question. An ideal gas occupies a container of volumes 4.5 into 10 to the centimeter cube at a pressure of 2.5 into 10 to the power 5 Pascal and a temperature of 290 Kelvin. Show that the number of atoms of gas in the cylinder, in the container is 2.8 into 10 to the power 23. It's pretty simple. Use PV equals to nRT and then simply convert the mole number with Avogadro's constant, multiplied by that, you get this number. In B, it says atoms of a real gas each have a diameter of this much meter. So they, since they have used the term diameter, it is implied we are considering all of those atoms to be spheres. Estimate the volume occupied by this many atoms of gas. Now, this is the part. Volume occupied by this many atoms of gas means you have to think what is the exact volume occupied by all of these atoms if they were perfectly stacked with each other, or let's say if they produced a solid object when their borders are touching each other. So it's pretty simple. You can calculate the uh, you can calculate the cubic volume, assuming all the spheres are stacked onto each other, or you can calculate the spherical volume and then multiply it by the number of things. So both of the approaches are acceptable, because if we place spheres one on top of each other, pretty much like the sodium chloride crystal, although there will be some in between space between the two atoms, but to occupy them properly, you have to occupy that space as well. So what I'm trying to mean is that, let me just draw it for you. If you have a cubic sphere, I mean sphere is it? If you have a sphere which is stuck inside a cube, so if you consider that this is a certain atom, so I've drawn this cube shape for visualization of the space around. But if you consider that all of these spheres are stacked one on top of each other, let's say one and the sphere is over here, and the sphere is over here, and the sphere is in front of here, for example, let's say right up over here, the other one is behind that. So whenever the spheres will be touching each other, the interspherical gap would be equal to their diameter. So although these corner spaces are going to be empty, but you cannot have the sphere stack onto each other, stack onto each other without having that space. The reason I'm trying to tell you this is that for this question, if you consider that the diameter is basically the side length of this cubic space, and simply go by calculating that the actual volume occupied or required for accommodating one atom of the gas is actually the cube of this diameter. So let's say this is the diameter. So if we go for that, d cube is the volume required to occupy a gas atom. That's okay. If you don't want to go for that, if you want to go for 1/6 pi d cube, 1/6 pi d cube is basically 4/3 pi r cube converted for the diameter formula. So that is also equally acceptable. So you can go by either way. The examiners are not going to mind. Now we can calculate what is the actual volume of all of these gas atoms altogether by this basic multiplication. Then number 2, it says, by reference to your answer in 1, suggest whether the real gas approximate to an ideal gas. Now this is the important bit. Whether a real gas approximate to an ideal gas. This means that whether one of the ideas for our ideal gas assumption was that the volume of ideal gas particles altogether is negligible compared to the container volume. So we're going to have the volume of the total volume of the ideal gas atoms altogether, their exclusive volume, and the question actually gave us the container within which they were kept. This was this much. So we're going to get this in meter cube. This was given in centimeter cube, but you can convert this into meter cube for your purpose. So it's important that you within your answer you convert both of them in the same unit so that you can do a numerical comparison. So either convert this into centimeter cube or convert that into meter cube, however you feel like. And what you can show that this volume calculated, which is actually occupied by the physical volume of the atoms, is going to be way too small, like orders of magnitude small compared to the volume occupied by the internal volume of the container where the gas molecules were actually kept. And that basically goes on to show that container volume is too large compared to the volume of the gas molecules, or in other terms, that an ideal gas approximation does apply to real gas, provided we consider the volume too small. If I have a look at the mark scheme to find out the answer, I can actually, without doing the math, I can show you the comparison. Number 18. You can see over here that volume can be directly done by cube. or you can directly go by 4/3 pi cube. So both of these approaches are equally acceptable. And then you just have to say that 4.5 into 10 to the centimeter cube is way too big compared to 0.48 centimeter cube. Our ratio of the volumes is about 10 to the power minus 4. Justified because volume of the molecules is negligible. So first you have to show a comparison, and there should be a numerical value supporting your answer. And then you have to write a statement for your justification that volume is molecule is negligible. So it does approximate the behavior of ideal gas.
স্যার
Yes.
স্যার ওই যে B1 এ আপনি কি বলছিলেন যে আইদার আমরা অ্যাটমস গুলোকে কিউব হিসেবে ধরতে পারবো অথবা স্ফিয়ার হিসেবে ধরতে পারবো।
Yes.
আচ্ছা স্যার।
Did you understand why?
Yes স্যার।
Okay. আচ্ছা, আমি নাম্বার 19টা করে দেখাচ্ছি because of this question. This can be tricky. Question 19টা আমরা দেখি। Question 19 এতে বলছে state what is meant by the internal energy of a gas. Pretty much definitive question. So be careful to write the word some and microscopic. And these are the two keywords students usually miss at least one of them to lose 1 mark over here. And then you go for the definition. Number B says the first law of thermodynamics may be represented by the equation del U equals to Q plus W. State what is meant by each of the following symbols. Be very careful to not to mess up the preposition. If I was writing the answer, I'm going to write it this way. Plus delta U means increase in internal energy of the system. Plus Q, heat energy supplied to the system. Plus W, work done on the system. And then number C, it says an amount of 0.18 mole of an ideal gas is held in an insulated cylinder fitted with a piston, as shown in figure 2.1. Atmospheric pressure is 1.0 × 10⁵ Pascal. The volume of the gas is suddenly increased. Suddenly, key, very important word. Suddenly is gonna cause the process to be an adiabatic process. You don't know what that word is. It simply means that the process is gonna be so fast that the heat energy of the no heat energy of the system can leave from the system, or no heat energy from the outside is gonna get into the system. So only the work done or physical work done is gonna be our actual energy input or output. That's the key idea for suddenly. The volume of the gas is suddenly increased from 1.8 into 10⁵ centimeter cube to 2.1 into 10⁵ centimeter cube. So we increase the volume. For the expansion of the gas, calculate the work done by the gas and hence show the internal energy changes by 30 joule. This is actually pretty simple. Atmospheric pressure is 1.0 × 10⁵. The piston went out to increase the volume inside. So delta W is always calculated by P into delta V. If you wonder why should it be constant P, should it be less than constant P? The idea is that because we are doing the process really fast. Am I thinking it right? Yes, because we're doing the process pretty fast, so there wouldn't be enough time for the pressure to be equalized. So we can consider that the pressure remains constant, only the volume undergoes a change. So we are assuming that the pressure for which the piston is actually pushing outwards, that atmospheric pressure against which the piston should move outwards, that remains constant. So this is atmospheric pressure. This is not the inside pressure. Try to understand. This is atmospheric pressure. So this is the pressure outside the piston, which is pulling from the outside, pushing from the outside. So when we're going to push the piston outwards, we are going to push the atmospheric particles outwards under a constant pressure, because atmospheric pressure is pretty much constant no matter what we do. And unless there is a large explosion or there is a shock wave, shock waves can actually produce a significant variation in atmospheric pressure, localized atmospheric pressure, that is. But that's not the case over here, so we're not going to bother for that. The volume of the gas suddenly increased from this much to this much. So delta W is P into delta W. So let's go for this calculation. 1.0 into 10⁵ multiplied by 2.1 minus 1.8 into 10 to the power minus 3. It becomes 10 to the minus 3 because I'm trying to convert this into meter cube. So centimeter cube converts to meter cube actually is 10 to the minus 6. So I did the multiplication in my head and put that number. See how much you get from here. This is going to be 0.3 and we're going to have 100. 0.3 into 100 gives you 30. Oh, that's 2. Now comes the interesting part. Determine the temperature change of the gas and state how whether the change is an increase or decrease. So how can we find out the temperature change of this gas? Ideal gas follows the ideal gas equation. So you don't have to write this. I'm just writing this to show you what formula am I using. This would lead us to get P1 V1 by T1 should be equals to P2 V2 by T2. Can we do that actually? We cannot, because we do not know the inset pressure variation of this thing. Hmm. 3 by 2 kT, half mc square equals to 3 by 2 kT. Okay, let's try it in a bit different way. এই ইকুয়েশন দিয়ে হবে না, এই ইকুয়েশন দিয়ে কেন হবে না বলতেছি। I tried this one but I can see that I don't have enough information for this because this pressure and this pressure, these are the inside pressure of the gas itself. This question doesn't give me the value of the pressure variation within the question. It only gives me the pressure outside the cylinder, which is the atmospheric pressure. So I do not have this data available to me, so I cannot do this math by this mechanism. I cannot. So this is not helping. So let's try something else. And now because I cannot work with this one, so I now have to think that what other equation do I know that relates energy with temperature. So I recall that the total kinetic energy of a certain amount of gas is given by a measure of temperature. So we actually came across one of this formula that half mc square, it is the average kinetic energy of a ideal gas molecule or particle, is given by 3 by 2 kT. Do you guys remember this equation? Anyone?
Yes, sir.
Half mc square equals to 3 by 2 kT. If you look back in the lecture or look back in the notes, you're gonna come across this equation. So if I just multiply the number of particles, total number of particles on both sides. So this is let's say the total number of particles, and this is the total number of particles. This actually converts the total K of the gas, because n number of particles having each average this much kinetic energy, which is pretty much the only, not pretty much, which is the only type of energy ideal gas particles are going to have, because ideal gas particles don't have any potential energy within themselves whatsoever, which is going to convert into 3 by 2 RT. Now K into N, no, actually I'm messing up something.
I convert করতে হলে মানে 6 মানে number of particles দিয়ে করতে হয় নাকি Avogadro's number দিয়ে করতে হয়?
হ্যাঁ এখানে ভুল করতেছি, দাঁড়াও K equals to হচ্ছে R divided by NA. So I'm gonna get R divided by NA over here into T. I'm gonna need the mole number. Do we have the mole number over here? We don't actually need that. What am I doing?
Yes, sir, mole number আছে।
আমাদের actually এটা লাগবে না, মানে I was trying to get into a complete equation, but practically we don't need that. I'm going to show you why we don't need that. The whole equation over here, which I'm going to get, is the total kinetic energy contained within the gas, ideal gas amount, can be given by 3 by 2 K N into T. So as long as you have a fixed amount of gas, fixed number of gas, because if you consider N is a constant, because we are not actually leaking out or entering new gas particles within this cylinder in the process that we are describing right over here. So N is a constant, K is a by default constant, 3 by 2 is also a constant, which actually gives us this relationship that total kinetic energy of a certain gas would be directly proportional to Kelvin temperature. Now does that help me? delta K is proportional to delta T. ঠিক আছে, delta K equals to no. Do I have the number of gas particles over here by any means? Yes, we have the amount of gas. I did not see this information. This is gonna come in really handy right now. Okay, beautiful. We have this. We have everything that we need. So this is gonna lead up to that delta K, change of kinetic energy, is gonna be 3/2 K N into delta T. So kinetic energy is going to be directly related to the temperature variation. So in this case, the kinetic energy increase is going to be 30 joule because we actually caused this kinetic energy. We actually pull the gas out. So if you think about from this equation, I'm going to talk about the plus or minus value after a while. Let me just do the math first. So 30 equals to 3/2 K into N into Na into delta T. So delta T is going to be 30 divided by 3/2 into K into 0.18 into 6.02 10 to the power 23. Yeah, the product of these two actually gives us R. So K into Na is actually R. So I could actually write R NR delta T. That could also work. I don't know why didn't I do that. Let's have a calculation for this. I might be wrong. I'm not sure if this is gonna work out right, but I hope this is right. কত আসে?
13.4 আসে।
মিলে?
না স্যার, mark scheme 20.0. Mark scheme for some reason ওরা 3/2 টাকে consider করে না। It's just an NRT. Delhi is equal to NRT.
কিন্তু কেন?
Potential part 1 এ তো আমরা ইন্টারনাল এনার্জি বের করেছি, তাহলে গ্যাসের কি পোটেনশিয়াল এনার্জি?
হ্যাঁ, আইডিয়াল গ্যাস বলে দিচ্ছে না, প্রথমেই তো বলে দিচ্ছে যে we have a certain amount of ideal gas held in the context. So potential energy তো এমনিতেই zero. So whether we take whether we energy put into the system or whether we take away from the system, this will be all related to the kinetic energy content of the whole gas molecules. বুঝছো?
জি স্যার। আর স্যার এক্সপ্যান্ড মানে পিস্টন ভলিউম পিস্টন স্টেশনারি ছিল, তো যখন পিস্টন স্টেশনারি ছিল তখন গ্যাসের ভিতরে আর বাইরে প্রেসার সেম ছিল না, অ্যাটমসফিয়ারিক প্রেসার।
We can assume that, but should we assume that? For all I care, the piston could be held in a, but the question says that an amount of 0.18 mole of an ideal gas is held in an insulated cylinder fitted with a piston as shown in figure 2.1. It doesn't say in equilibrium, it said it is held. So the wording can mean, I mean, I wouldn't say would mean, this wording can actually mean that the piston was actually held by some physical force. So there might be some inward force, there might be some outward force. I don't know. Why shouldn't we consider 3/2? N equals to half mc square equals to 3/2 K. Half mc square equals to 3/2 K temperature. Number. মার্স কি মোরা 3/2 ইউজ করে নাই, কেন করে নাই? বিপদে পড়া গেল তো। কত নম্বর কোশ্চেন এটা? 19। Delta E equals to NR delta T decreases. Okay. The calculation of work done successfully attempted by most candidates, although some had declined substantially the volume of milligram of the centimeter who went on to explain that the work done by the gas is the change in internal energy because there is no heat supplied to it. Oh, acha, you have to mention this as well. I did not talk about this line. If you don't write this line, you're not going to score 3 marks out of it. Yes. Yes, I actually forgot to talk about this specific line. You have to look in the question in number 1. It says, hence show that the internal energy change is 30 joule. I only calculate delta W is 30 joule, and then I moved on to this part. You have to say that because no heat energy was supplied or left from the system, so Q is 0. So Q is 0, which means delta U equals to W. So ওইখান থেকে আমাদের 30 joule যে আমাদের delta U হবে এই হিসাবটা ওইখান থেকে আসবে, সেটা বলা লাগবে। আচ্ছা, to those unfortunately the information provided in the question was insufficient for a correct calculation of the required temperature change. Yes, this section of the question was not included in the overall assessment. This is the first thing that I told you, that we do not have enough information to go for the calculation. So this is actually a goof up calculation. বুঝছো কি বলছি? এটা properly calculate করার জন্য আমাদের necessary data আরো লাগবে, because we did not know, the question doesn't specifically tell us what is the pressure variation within the container. Without having it known, it is not actually truly possible. I had a hunch this was the case. But then again, let's say we have the same question. If we assume this question to be fulfilled or sufficient, why would this mechanism not work? I mean, number of molecules into half mc square gives us the total kinetic energy content of this thing, and the variation of kind of kinetic energy is going to be transferred into the variation of temperature change. All of this equation looks logical, right? But for some
Yes,
reason
sir.
they did not consider 3/2 within the part. এই কোশ্চেনের পাশে একটা স্টার কি বলে একটা ক্রস মার্ক দিয়ে রাখো, আর ওয়ার্কশিটের কভার পেজে একটু লিখে রাখো যে এই কোশ্চেন নাম্বার 19C2 নিয়ে একটু রিসার্চ করা লাগবে। I'm going to look into my capabilities to talk to other teacher or internet groups about this problem. But as far as I am concerned, I think this mechanism actually makes sense. I'm pretty sure this makes sense. This was not supposed to be that. But however, I'm going to tell you about this part, whether the temperature change should be more or less. What you need to understand that now we're gonna, so as we push the piston outwards pretty fast for as per the question, the intermolecular spacing of the particles is gonna be more. So you have a look over here that by pushing it out, we were doing some negative work on the gas, because the way it always works is that if we squeeze up a certain amount of volume of gas, we do physical work on it because we work against the pressure of the gas. But if we expand a certain amount of gas, the gas itself does the work against the pressure of the outside. So whenever the piston was actually suddenly pulled out, so the volume of the gas was suddenly increased, we can assume that this gas actually pushed out the cylinder outwards, which means this 30 joule of amount of energy was actually leaving from the gas to the atmosphere, because work was done on the atmosphere, work was done by the gas. So energy is leaving in the form of work from within the gas, which means that delta U would be negative, because W is negative, so delta U should also be negative, which actually means temperature should fall. This is a physical explanation, but they actually didn't ask for an explanation, because they just only asked that determine the temperature and state whether the change is in increase or decrease. So all that you have to ask for what it is going to be, but I explained it to you so that you understand what it is, and if it ever comes, just sit and explain so that you can also write it. If I was trying to write the state and explain question, this is how I would write it. sort of a final version, is that piston moving, volume of the gas increase means work was done by the gas, in which case W in the equation is negative, which also causes delta U is negative, means internal energy of the gas decreases, hence temperature also decreases. বুঝা গেছে? Should I say it again?
That's your business.
Try to write in a sequential pattern that one of the stuff lead to the other stuff in a logical manner. So the examiners actually find this stuff pretty good. If you can write in a logical manner, the examiners know that you actually know how to do this. Okay, I'm going to do question number 20B. This is actually one of the interesting questions. We have to fill up a certain table, and this mark scheme for this answer is absolutely messed up. As far as I remember, the mark scheme is wrong. I'll show you why.
Sir, confusion আছে last question related.
কোনটাতে?
Sir, গ্যাসের volume, yes sir, last time.
বলো।
Sir, volume তো increase করছে, that means gas work করছে। যদি gas work করে তাহলে তো সিস্টেমের উপরে work করে না, তাহলে W
বলতেছি, in this question, I mean, this within this equation, delta U is the internal energy increase of the system, Q is the heat supplied to the system, W is the work done on the system. So this would mean that if we have a system over here, if it receives Q amount of heat and if it also receives W amount of work, together they're going to cause delta U amount of internal energy increase. This is the significance of this question. এখন এই ইকুয়েশনের মধ্যে W মানে হচ্ছে work should go into the system. But as per the question, it says the volume of the gas suddenly increased from this to this. তার মানে কি আমাদের এই পিস্টনটা বাইরে দিয়ে গেছে, so the inside volume of the gas got increased, right? When the gas inside the cylinder got increased, it had to actually push out the atmospheric particles over here to move out. ঠিক না?
yes sir.
So as the gas increases in volume, it pushes out the atmospheric particles to make its own volume, to make its own space required. In this process, work will be done on the atmosphere because atmospheric particles were pushed out. So work would be done by the gas on the atmosphere.
আচ্ছা স্যার, এখন বুঝেছি।
Beautiful. ওই জন্য এখানে W টা হচ্ছে নেগেটিভ. It means in this case work was not done on the gas, or work was not actually entering into the system, rather work was leaving from the system because work was done by the gas on the atmosphere. Let's look at this next question. এর পার্টগুলা হচ্ছে সব descriptive part. I want you guys to try it. If you can solve it, or if you have some question regarding the examination for the mark scheme, ask me later on. No video, I'll help you to explain it better. I'm jumping to B number question. It says a fixed mass of an idle gas undergoes a cycle's PQRP of changes as shown in figure 2.1. Calculate the work done on the gas during the change from P to Q. Acha. It actually pretty simple. Within the variation PQ, we have a constant pressure. You can read off the pressure from the x-axis. I think this is gonna be 4 into 10 to the power 5 Pascal, and the volume change is gonna be 8 minus 2 into 10 to the power minus 4. So what you should see that in this case, the volume of the object is becoming smaller. Have a very good look. Initial volume at P position was bigger, and the final volume is smaller, which means the gas is becoming squashed, or its volume is decreasing, which means external force is causing it to become volume smaller. So this would mean that work is being done on the system, or W for the equation is actually positive. So calculate the work done on the gas during the change from P to Q. This is actually P into delta V. You can calculate this out. I am not willing to do that, so I'm gonna just copy the answer from the mark scheme. 240 joule. This is gonna be 240 joule. Now, here comes this next table. What is the on the key part that you need to make sense? That once we complete a full cycle using the same gas, we actually will, for example, let's say if we make the amount of gas go through the cycle P, Q, R and back to the P position, we are getting back to the same combination of pressure and volume and temperature. This actually means that when one full cycle would be completed, the total change of internal energy would be 0. এই জিনিসটাকে বুঝো। Whenever we take it from one pair of one set of values of PVT to another set of PVT, we might actually put in some energy, we might give away some amount of energy. But eventually, if we complete one full cycle, it basically means that we come to the original state, or the total internal energy change for this whole cycle is to be 0. Pretty much like the idea of displacement. এই কনসেপ্টটা আমাদের ফার্দার ম্যাথমেটিক্স জন্য অনেক বেশি ইম্পর্টেন্ট, বিকজ হ্যাভ আ লুক ওভার হিয়ার, লেটস সে we are going to fill this up. The question says some energy changes of during the cycle PQRP are shown in figure 2.2, and we have to fill this up. Come figure 2.2 to show all the energy changes. Now try to understand what is happening. This question says work done on the gas and heat supplied to the gas and the total increase in internal energy, which means for each of these processes, according to the first of thermodynamics, the sum of first two column should be equal to the third column. এই জিনিসটাকে ভালো করে বুঝো। এটা হচ্ছে আমাদের W, এটা হচ্ছে আমাদের Q, এটা হচ্ছে আমাদের ডেল্টা U। এই কলামের রিলেশনশিপ গুলো বোঝা যাচ্ছে কিনা?
Yes, sir.
ঠিক আছে। সো P থেকে Q তে আমাদের ওয়ার্ক ডান অন দ্য গ্যাস আমরা এইমাত্র ক্যালকুলেট করলাম, সেটা ছিল হচ্ছে 240 joule. So it was actually done physical work on the gas. So I'm going to write plus 240. This is minus 100, minus 600. So how much you're going to get from here? It's going to be minus 360. On Q2R, we are applying no work done, but we are supplying a huge amount of heat to the system. So this is going to be plus 720 as well. Now comes the interesting idea. To fill up this part, we cannot do this right away. The information that we have to take care that in the whole process of the cycle PQRP, the total amount of increase in internal energy should be 0, which means that total sum of these three values, if you sum all of these, that should be 0. So basically what I'm trying to say, that if this is an unknown, let's say this is X, this would mean that minus 360 plus 720 plus X, whatever that X is, should be equal to 0. তাহলে এখান থেকে X এর ভ্যালু কত আসবে?
360.
360 আসবে?
Gee, sir.
Okay, fine. So this is gonna be plus 360. Plus or minus? I think minus. Minus, huh? So this is gonna be minus 360. So the total change in internal energy for the entire cycle, once we get back to the P position, should be 0. এখন তুমি এই পার্টটা খুব ইজিলি ফিল আপ করতে পারবা। এখন তুমি চিন্তা করো যে এইটা প্লাস এইটা করে 360 মাইনাস 360 হইতে হবে, তাহলে এখানে কত দরকার? It should be the sum of these two numbers. So 480 plus 360.
120.
No. Try to understand. Let's say if I give a variable y plus 480 equals to minus 360. Work that up. Y plus, I'm using y just to differentiate between the two unknowns that I'm trying to define. This much should be equals to minus 360. তাহলে y value কত হবে?
Minus 840.
Minus 840. So this should be, this is my best guess for the whole table, but if you look at the mark scheme, you'll see all messed up numbers, and I'm going to explain why that is. So 240 is good over here, heating was 0 over here, and they gave 240 over here as well. So the problem that we have is that in this whole thing, they gave us different heating supply to the gas numbers over here, but in the mark scheme they used some other numbers. Do you see that? But the logic that we used for this whole process pretty much remains the same. If you check for all the rows, 240 plus 0 equals to 240, 0 plus 320 equals to 320, minus 560 plus 0 equals to minus 560. So for all the horizontal rows, first column plus second column equals to third column makes sense. For the third column altogether, the total sum of these three numbers is also 0, which is also the logic of how this problem is to be solved. But because they messed up the numbers over here, all of these other numbers are also showing up to be different. Actual question had 600, 120, and plus 480, but whether in this case they use 0, 320, and 0. So I don't know what happened to the mark scheme, or whoever made the mark scheme, what happened to them, but this mark scheme is not essentially correct, but the logic they have used is very much obvious and hiding in plain sight, which is pretty much how we solve the problem. বুঝা গেছে কিনা?
এটা কি real mark scheme-টা, sir?
Yep. If you have a look at the explanation, it says, in some schemes, no mention was made to the fact that the potential energy between the atoms or molecules of an ideal gas. What? Yeah. This is B2. Oh, sorry. B3. I'm to A3 board this. B3 says, in general, changes P to Q and Q to R were shown correctly despite having answered in B1. Despite having answered B1 correctly, it was usual to find that the values for the change in energy did not add up to 0. So they just gave a very basic marking for how the problem to be solved, but pretty much there's a problem that they messed up these numbers over here. I think whoever wrote this mark scheme actually did some observation error. That's my best guess. I'm not sure about it, but that's my best guess. So that's why their values are altogether messed up compared to the actual question. Moving on. 21 Parba. I mean 21 is C-টা করে দেখাবো. It's an important question, especially C2-টা. বলতেছি আমি, খেয়াল করো. Have a look. Question number B says, use equations for the pressure of an ideal gas to deduce that the average translational kinetic energy EK of a molecule in an ideal gas is given by the expression EK equals to 3/2 RNA R divided by NA T, but R is the molar gas constant, NA is the Avogadro constant, T is the thermodynamic temperature of the gas. এটা করা খুব ডিফিকাল্ট না, আমরা এটা নরমালি ডেরিভেশনটা দেখালে এখানে পারবো। PV equals to 1/3 mc স্কয়ার থেকে শুরু করতে হবে, আর হচ্ছে অ্যাভারেজ কাইনেটিক এনার্জি ইকুয়ালস টু হাফ mc স্কয়ার থেকে বিং অ্যাবাউট করতে হবে, তারপর আস্তে 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 চেঞ্জ করতে করতে এই জিনিসটা চলে আসে। সিতে বলছে a deuterium nucleus H21 and a proton collide, a nuclear reaction occurs represented by the equation. So we are having deuterium nucleus, which is hydrogen 2, and a proton, which is basically hydrogen 1. They are colliding and producing a helium 3. Along with, we have some gamma photon. Statement is then whether the reaction represents a nuclear fission or nuclear fusion. Well, it's obviously nuclear fusion. I'm going to write nuclear fusion, full stop. That's the straight answer. Then you have to write that here the smaller particles or smaller nucleides are merging together to produce a bigger nucleid. So it's a nuclear fusion process. Number 2, for the reaction to occur, the minimum total kinetic energy of the deuterium nucleus and the proton is 2.4 × 10⁻⁴ joule. Try to understand the significance of this sentence. For the reaction to occur, the minimum total kinetic energy of the deuterium nucleus and the proton is this much. So together they have to have this much energy. The question doesn't specify that which one should be there. So one can be stationary, the other one can be moving. Both of them might be moving. They might be moving in the same direction, opposite direction, doesn't matter. But altogether, we need this much kinetic energy for the reaction to occur. Assuming that a sample of mixture of deuterium nuclei and protons behave as an ideal gas, calculate the temperature of the sample for this reaction to occur. এটা তো অ্যাকচুয়ালি খুব কঠিন না, খুব কঠিন কি? It might be, I'm not sure. দেখি. So we just derived this equation that average kinetic energy is gonna be 3/2 R by NA into T. So this is the average kinetic energy of two molecules. আচ্ছা না, এখানে তো কঠিন কিছু দেখতেছি না। Why did I pick up this question? Proton and deuterium nucleus will have equal kinetic energies. We have to divide the kinetic energy amount by 2. This is the key part. Yes. So let me explain. The question says that the minimum total kinetic energy of the deuterium nucleus and the proton is to be this thing. And then comes the idea. Assuming that a sample of mixture deuterium nuclei and proton behave as an ideal gas, in which case all the particles are considered to be identical to each other. So you have to consider that if you have two particles, let's say one is helium nucleus, one is the hydrogen 2 deuterium, the other one is proton, and you have to consider they are identical, and the total kinetic energy is this. So the average kinetic energy of one of these particle should be half of that. That's the key part. So to solve this problem, you have to divide the total amount of energy of both the particles by 2 to be applied within that equation. আচ্ছা এটা ছিল হচ্ছে tricky part, যে আমাদের এখানে deuterium nucleus এবং proton nucleus or proton কে we have to consider them to be identical particles, assuming they behave as an ideal gas, and divide the total kinetic energy of both of them simply by 2 to convert it into the kinetic energy of a single particle and go on from there. এই জিনিসটা আমার বরাবরই ভুল হয়, হয়তো এবং হয়, এবং আমি এখনো ভুলে গেছিলাম যেটা কি করতে হয়, so I have to look up the mark scheme, but I still remember that there is some key thing to follow in this question. The rest of the part is pretty simple. Just place the numbers, do the calculation, and eventually you get this thing. Use of E equals this much, giving 1 per mark, score 1 mark. So if someone does not forget to do the division, they're still going to score 1 mark because they would know how to do the calculation, but they're not only going to score 1 mark out of 3 because they would miss out the problem. That is the total energy of two particles, whereas in the equation EK, this is the average kinetic energy of one particle. So if someone forget to compare these two variables, they're only going to score 1 mark. Pretty logical. The examination report says actually number 2. Very few candidates realize that a deuterium nucleus can be assumed to have the same average kinetic energy as a proton, that is 1.2 into 10 to the minus 14 joule. Okay. এরপরের কোশ্চেন হচ্ছে, আমি আস্তে আস্তে আগাচ্ছি, তো তোমাদের কোথাও কোনো কোশ্চেন থাকলে আমাকে জিজ্ঞেস করো। যেমন নাম্বার বি একটা খুব ভালো কোশ্চেন, 23। কোশ্চেন 23টা একটু দেখি আমরা। 23 বি কি কেউ করছো up so far? Anyone? I'll give you some time to attempt this question. আমি এটাও আলাপ করব, so forget about A. এটা এখন মাথায় নেওয়ার দরকার নাই। বি নাম্বার কোশ্চেনটা পড়ো, এই প্রবলেমটা কিভাবে সলভ করার জন্য অ্যাপ্রোচ করা যেতে পারে সেই মেথডোলজিটা একটু চিন্তা করো। I'll be right back. Do you kids hear that sound? Recording is progress.
Yes, sir.
Yes, sir.
Oh,
Yes, sir.
pretty loud sound. Anyway, so yeah, question number B. Try to understand the content of this question. A jeweler wishes to harden a sample of pure gold by mixing it with some silver so that the mixture contains 5% silver by weight. The jeweler melts some pure gold and then adds the correct weight of silver. Try to understand. The initial temperature of the silver is 27 degrees Celsius, which is pretty much a room temperature. Use the figure of data in figure 2.2 to calculate the initial temperature of the pure gold so that the final mixture is at the melting point of pure gold. Have a look at these problems. Gold has a melting point of 1340 Kelvin. Silver has a melting point of 1240 Kelvin. To make sense with the problem, let me just write up this temperature, which is relevant for this question. Let's say over here by a vertical scale. So if I represent this thing over here, the smallest temperature that we will have to deal over here is the initial temperature of the silver, which was only 27 degrees Celsius when we added it into the mixture. So in Kelvin, this is going to be 27 plus 273, 300 Kelvin. This is the smallest temperature, 300 Kelvin. 300 Kelvin. This is the temperature of the solid silver piece that we're going to add into the gold. The aim is that we are going to add this piece of silver into the gold with appropriate weight, such that the temperature of the gold should drop down and the temperature of the silver should rise up, and then it should melt at some point, which is 1240, which I'm going to label afterwards. But eventually, when the temperature exchange is done, I mean, silver is done heating up, melting, and gold is done cooling, the final temperature of the mixture should be the melting point of gold. So this should be 1340 Kelvin. So obviously,
স্যার বুঝিনি
বলতেছি আমি, কোশ্চেনটা খেয়াল করো। The jeweler melts some pure gold and then adds the current weight of silver. The initial temperature of the silver is 27 degrees Celsius. This is the last line, which is really important to understand. Use the data to figure 2.2 to calculate the initial temperature of the pure gold, so that the final mixture is at the melting point of pure gold. So we're gonna mix some room temperature silver piece with some molten gold, so that after the mixture is done, final temperature of the mixture basically means the equilibrium temperature of the mixture. So when the cold object is done taking heat and the hot object is done giving up heat, and both of the temperature comes at the same point, according to the question, that final temperature is supposed to be the melting point of pure gold. So this is supposed to be a final temperature of the mixture. Doesn't this obviously mean that at the point when we actually added the silver, that temperature of the pure gold should have been somewhat bigger?
Yes, sir.
So এটা হচ্ছে আমাদের problemer visualization. That's the way I usually do. So this is the temperature that we're asked to find out, and obviously there is another temperature that we have to mark, which is the melting point of silver, which is 1240 Kelvin. So try to understand what is about to happen over here. This is the key part that you need to understand. In terms of mass, for a 100% material in our mixture, we're gonna have 95% gold plus 5% silver. এটা কি বুঝতেছো কিনা দেখো?
Yes, sir.
That's the very first thing. And then whenever we're gonna mix them up, the temperature of liquid gold is gonna only drop from a high temperature to the melting point, whereas the temperature of the silver piece is gonna rise up in the solid state, which is basically the same. They have given us any value for solid or liquid state, so basically we can consider the same value. So the solid silver rises up to here, reaches up to this point, then it melts, and then rises its temperature from here all the way up to 1340 as well. So the heat absorption of the silver piece happens in 3 stages. Temperature increase in solid state, step 1, melting, step 2, temperature increase in liquid state, step 3. So these are the 3 individual parts for the silver piece, whereas the gold only loses heat in its liquid state from the high temperature, dropping to 1340. This is supposed to be our final temperature, and we have all the relevant values that we have over here so that we can use it for our calculation. So I'm going to build up the equation over here and I want all of you kids to see and check whether you can make sense out of it. I'm going to keep that in view. Make it a bit bigger. Yeah, that works. So let's say I'm going to write the heat absorption first. So 5 parts of silver is needed. So I'm going to write only 5 over here. Gram, kilogram, not necessary. It's the percentage. So for every part of 5, the gold would be 95. So you can do it in kilograms, you can do it in ton, you can do it in microgram, milligram, picogram, whatever. But the percentage would maintain the ratio same. And actually, I'm writing this side for the silver. I'm writing this side for gold. This is the heating up, this is the cooling down. This is the heat absorption, this is the heat giving up. What is release, heat release. So the reason I'm writing in three parts, because for this case, silver is having the same specific heat capacity for both in solid and liquid state, which is good. But in many cases, for certain materials, it can be different. For example, water in its three different state has three different values of specific heat capacity. Solid ice has a specific capacity of about 2100 joule per kg per Kelvin. Liquid water has 4200, double of that. Whereas steam has about 1200. So it's not necessary for this math to write these two parts in different expression, because we have the same value of C, specific capacity. But learning to do this in this manner can save you some future problem, provided the materials or different state of the same material do not have the same specific heat capacity. So I'm gonna write the values over here. So 5 into, how much is that? 235 joule per kg per Kelvin, whereas specific heat is given in kilojoule per kg per Kelvin. Very important. So whenever we're gonna place these numbers, you have to include into 10 to the power 3. So 5 into 235 into 1240 minus 300 plus 5 into latent heat of fusion 105 10 to the power 3 plus 5 into 235 into 1340 minus 1240. This is the total heat absorbed by the silver piece, should be equals to 95 fraction of gold 129 into unknown temperature theta, which we want to find out, minus 1340. এই পুরো ইকুয়েশনটা এখন আস্তে আস্তে সলভ করো, সলভ করে থিটা ভ্যালু বাই করো, বাই করে বলো কত আসে। ডু ইট।
Do it!
Did any of you see that full video of Shia LaBeouf? Yes, you can. And stuff. Maybe not. আচ্ছা, এটা করে দেখো, বল আমাকে থিটা ভ্যালু কত আসে, তাহলেই হবে। Where did Rifat go? He left.
স্যার আমার এসেছে 1482.6.
Okay, that's one answer. So look at the mark scheme. কত নম্বর ছিল জানো এটা? 23.
23B.
1483, yeah. Well done. প্রসিডিউরটা বুঝা গেছে কিনা? এই কোশ্চেনটা
Yes, sir.
practically, if you ask me, it's not difficult. But it's not difficult in terms of the math that you have to do, but it's difficult in terms of retrieving the actual information out of the question, because this last line can be difficult for you to make sense. Read it again. Use the data of figure 2.2 to calculate the initial temperature of the pure gold so that the final mixture is at the melting point of pure gold. এই কথাটুকু পরে আমাদের অনেকগুলো জিনিস অটোমেটিক্যালি বুঝতে হবে। সেটা হচ্ছে আমাদের ফাইনাল টেম্পারেচার পিওর গোল্ড হইতে হবে, তার মানে হচ্ছে আমাদের ইনিশিয়াল গোল্ডের টেম্পারেচার পিওর গোল্ডের মেল্টিং পয়েন্ট থেকে বেশি হইতে হবে। You have to have that imagination or forethinking in your brain to be able to come up with this kind of a figure and ultimately to be able to build this kind of an equation. So this equation, once you build up the equation, the rest of the part is actually very simple. But building up this equation part by part actually can be slightly difficult. And that's one other thing that is important, is that the masses over here were not placed in actual kgs or grams. The masses were placed in terms of percentage. If you wonder that why should it work out, because we use all of these equations over here for joule per kg, and over here these are all kilojoule per kg. So shouldn't these numbers should also be in kg? The answer is they don't have to be. This can be 5 gram each, and this one can be 95 gram as well. If you're gonna have the both the units crossed off on both sides, ultimately your math is gonna work out just fine. This can be 5 kg and the other one can be 5 kg. And that can work out just fine. So converting the information of the percentage ratio into mass information is also another important bit for this problem. You can see that this problem actually has 5 marks in it. It's gonna be, well, in C, it says select a suitable thermometer for the measurement of the initial temperature of the gold in B. I'm gonna say radiation thermometer. Do you guys know what radiation thermometer is?
Not really, sir.
So that's it. These are the radiation thermometers. Basically, the thermometers that currently is in wide use to measure the temperature of people while aiming at your forehead. I mean, they're not touching you. So how do they know what is the temperature of your forehead just by aiming some gun type thing at your head? Idea is very simple. Our body gives out a certain amount of infrared radiation depending upon the temperature of our skin. So if the temperature of the skin is more than what it should be, it gives up more infrared radiation. So by measuring the infrared radiation coming off the skin for a specific amount of surface area, we can actually convert that amount of radiation information into relevant temperature. That's basically the idea of a radiation gun. This is also the process by which you could measure the temperature of sun or other celestial bodies, even though none of us have yet been into on that those locations actually or physically. So in my opinion, this and these things can actually work pretty well for cooking as well. In many cases, you can just have a you can aim this thing at the subject. But for cooking, actually, thermocol thermometers work even better, especially for the temperature measurement of thick cooking objects, for example, like steaks and lasagna. Yeah. How do you think some answer can look like this? Do you have any idea?
Lucky, sir.
These are actual answers from the mark scheme. CAE published mark scheme, by the way. These two are years, and this is a road with a Christmas tree in the back. I'll help you to solve this problem. এটা যেন কত নম্বরে ছিল? 2023 শুরুতে ছিল। Acha, I'm going to discuss question number 24 and then we can call it a day maybe. Question 24 is actually pretty simple, except for the examiners were vicious while they were setting up this question. And I'll tell you why I am using the word vicious in this question. Have a look. It's a pretty simple question. 6 marks, pretty rewarding question as well. But you can rest assured that you're not going to score at least 1 mark out of this question because of the type of the question that we have. Have a look. The first of thermodynamics may be expressed in the form delta U equals to Q plus W. U is the internal energy of the system, delta U is the increase in internal energy, Q is the thermal energy supplied to the system, W is the work done on the system. Pretty good. Complete figure 6.1 for both of the processes shown. Write down the symbol plus for an increase, the symbol minus to indicate a decrease, and the symbol 0 for no change as appropriate. Scenario. First of all, the question says the compression of an ideal gas at constant temperature. Well, we know for ideal gas, if the temperature is constant, then the total change of internal energy should be 0. So what you need to understand for this whole thing, that delta U should be equals to Q plus W. So this equation needs to be fulfilled at least in terms of increase and decrease. So if we are using an ideal gas maintained at a constant temperature, this should be 0, obviously. And because we are doing some compression, which means physical work is done, so work will be done on the system, so this should be plus. And if this has to be 0, I mean 0 has to be equal to some increase compensated by some decrease. So that basically makes sense. This will be minus and plus. Second row, the heating of a solid with no expansion. No expansion. No expansion means that it is not expanding, so it is not doing any work against the atmosphere whatsoever. No work is being done onto it either. So the physical work done on the system should be 0. It is heating, so heat is supplied, which ultimately means internal energy was increased. So plus plus 0. এটুকু পর্যন্ত কোনো ঝামেলা নাই, easily doable, makes sense. Come in the third row, the melting of ice at 0 degrees Celsius to give water at 0 degrees Celsius. Consider this, the melting of ice at 0 degrees Celsius to give water at 0 degrees Celsius. They've given us a note, ice is less dense than water. It's actually true, ice is less dense than water. This is why ice floats on water. Now, because you have this information, what you will assume that whenever the melting will happen, the volume of the melt water would be less than the initial volume of the ice, which means the total object is going to shrink in volume. If the object shrinks in volume, it means that external atmosphere has done some work on the system. So external atmosphere has done some work on the system to squash it down, which means in this case work will be done on the system, which should lead you to believe that this is supposed to be plus. এটা কি বুঝতেছো কেন প্লাস হচ্ছে? Ice is less dense than water, তার মানে হচ্ছে equal for, if you consider for equal mass, if this is the volume of ice, after it becomes water, this will be somewhat smaller, maybe not this much smaller, but it will be somewhat smaller. So this is ice converting into water. This is going to become something smaller in volume because less dense. So which means if you undergo a bit of a volume decrease, if work is physically done by the system onto the thing. That's the idea of volume decrease. And because we are doing some melting process, obviously melting means that we're going to have to supply heat to the system. So this is going to be plus as well, which essentially means that internal energy of the system should also increase. That's my best guess. Now look at the Mars scheme and find out for yourself what the Mars scheme has for you. What do you see in the Mars scheme? Have a look. Do you see? On the third row, third column, they have 0, which means they're assuming that there should be no volume change. And -1 for each error, which means you are gonna get 1 mark less for this last column. But if you have a good look over here, if they did not give you this note, just mention this one: the melting of ice is 0 Celsius to give water 0 Celsius. You wouldn't be bothered to bring this up in your head. This is a true fact, but I don't think any student would consider this volume decrease to be a significant margin. So they are more likely to give 0 over here if this information was not given. Provided this information is provided, it is essentially understandable that we should take care of this information. Don't you think? I would, if I was doing this answer. And if you do take care of this information, my essential, obviously, essentially, my answer would have been a plus sign over here, because that would represent a volume decrease in the melting process. But the examiners wanted 0 over here, while they additionally provided this note. So if I was answering this question, I would never get full marks for this question. I would definitely lose this mark, because I would definitely give plus over here, not knowing the mark scheme, if I was sitting for this question in an actual exam. So yeah, that's what they did. Have a look at the examination with the marks range from 0 to 6. The heating of the solid proved to be the easiest to answer correctly. The compression of the gas caused most problems. So they haven't mentioned anything about the water part. I mean, none whatsoever. Bad, but that's the way it is. তোমাকে বুঝছো কেন এই কোশ্চেনটা প্রবলেমেটিক? বলবান?
জি স্যার।
জি স্যার।
I mean, they could simply not give the note, and that would be perfectly all right. They give the note and give the answer 0, which are contradicting answers. But
distraction.
Yeah, and evidently derailing you from an appropriate thought process and making you lose mark. Ask you to talk. We're going to pick up more problems from the remaining part of the worksheet in the next class, inshallah. So if you can manage some time, do some problem on your own and bring up with some questions in the next class. Thank you very much. Assalamu alaikum.
Walaikum assalam, sir.